Chemistry 3101. This is chapter 15 in our continuation in chapter 15, and we are actually going to skip section 15.8, which deals with drawing an NMR of a compound. Now, here's my take on this section. I'm not going to ask you to draw the NMR of a compound. The reason why is when I first started teaching this class, I used to cover this section, and I had done paper quizzes before the pandemic where I asked my students to draw an NMR. Now, the problem with this that I found is that some students could draw really nice ones, and other students' drawing skills weren't quite as good, even if they may have understood the content. So some of the NMRs are really difficult to grade. And so here's, again, is my summary of this, is that I think this is an important section. In fact, I even assigned a couple of problems, or not assigned because they're not for point value, but I posted a couple of problems from this section in the practice problems that I recommend you take a look at, because it is an important skill to be able to draw an expected NMR of a compound. However, it's something that I'm not going to ask you to do on the quiz. All right, so let's move ahead to section 15.9, which is using proton NMR to distinguish between compounds. You take a look at these three molecules here. The first one on the far left, this is called orthoxylene. The next one is called metaxylene, and this one here is called paraxylene. They're all isomers of each other, right? They all have the same molecular formula. It's basically a benzene ring with two methyl groups on it. But if we look at the types of protons that are in each of these three molecules, you see that we end up with different numbers of signals in our NMR. Right, if we look at this first compound, and we could do the same thing with all three of them, we see that there is an axis of rotational symmetry such that the two methyl groups are chemically equivalent, so they would produce one signal. Likewise, the two blue protons are chemically equivalent, which produce another signal, and the yellow protons are going to produce a third signal because they are also chemically equivalent. We see the same thing applying here, right? We see the same thing applying here, that we have that axis of rotational symmetry, and that explains why the red protons are chemically equivalent, and that explains why the blue protons are chemically equivalent. However, the green and the yellow protons are not chemically equivalent, are they? Because you can see that this proton in green is next to the two methyl groups, therefore it's in a different environment, or a different electronic environment, than the proton in yellow. And if you look at the last one, well, we have two axes of rotational symmetry here, don't we? We have this one here that we could rotate 180 degrees, and we also have one going horizontally like this, where we could also rotate 180 degrees, and that's why we only end up with two signals. The two methyl groups are equivalent, chemically equivalent, and all four of the protons in blue are chemically equivalent. So even if you didn't know a whole lot about splitting, which we looked at last class, you could just say, well, I just look at the number of signals and I would be able to distinguish between these three compounds. So this shows you how powerful NMR is, how powerful a tool it is. Let's take a look at a question. This is question 15.21 from our textbook. It says, how would you use proton NMR spectroscopy to distinguish between the following molecules? If we look at A, we have two different compounds, and I just want to put this out there to my students. The question you might want to ask yourself is, how many signals would I see for A? Could anybody tell me for A, the first one that I have circled here in blue, how many signals you would see? How many unique types of protons are there in this molecule? And it's not a trick question. Yeah, somebody says that there's three types of signals. The reason why is there is an axis of rotational symmetry here, isn't there? So we see that this proton and this proton are chemically equivalent, as are this proton and this proton, according to that axis of rotation. But we also see that this methylene and this methylene are chemically equivalent. I don't know why I put a CH3. These two methylenes are chemically equivalent based on that rotational symmetry. So we would see three signals for this compound. Could anybody tell me how many signals we would see for the second compound? Give me an idea. Would there be more or less, maybe, if you're not sure exactly? Maybe another question we could ask is there an axis of rotational symmetry? And in this compound, there is no axis of symmetry. So that means that each one of these protons is going to provide a unique signal on the aromatic ring. This proton is different from this proton, which is different from this proton, which is different from this proton. All four of those protons on the aromatic ring are different. If you just look at the environment that they're in, they're all in very different environments. Now I have a methylene here and a methylene here. If think that by now it should be pretty obvious that these two methylenes are not chemically equivalent, right? One of them is right next to the carbonyl. The other one is another carbon away. So they're definitely going to have different chemical shifts. And so those protons, these ones and these ones, are not chemically equivalent. So let's tally up how many we have. We have 1, 2, 3, 4, 5, 6. We would end up with 6 signals in the NMR spectrum. And so the difference is the first compound would produce 3 signals and the second compound would produce double the amount of signals. Now I didn't give myself a lot of room to solve B, but if I redraw the structure of this compound here, so I'll just do it over here, the easiest way to distinguish between, come on, what's going on? There we go. The easiest way to distinguish between these two esters, right? These two esters have the same molecular formula, but they have different connectivity, don't they? First of all, this methyl group here is not split by any other protons, is it? That methyl group is going to have a chemical shift of 0.9. That's the baseline. Plus, since it's alpha to a carbonyl, I'm going to add 1 to it. So it's going to give me 1.9 ppm. I'll have a singlet that integrates for 3 protons. So this is a singlet, integrates for 3 protons at 1.9 parts per million. All of these protons in the tert-butyl group are also going to produce a singlet. They're going to integrate for 9 protons total, but what's their chemical shift going to be? Well, the baseline chemical shift of a methyl is 0.9, and you can see that we have the alpha carbon here and we have a beta carbon here. So they're beta to this oxygen of an ester. So we would add around 0.6 maybe. So this would be around 1.5 parts per million, roughly. Okay. You could even just distinguish between these two compounds just by analyzing the methyl that integrates for 3 protons. Let me prove it to you. Because if you analyze this methyl group that's also going to integrate for 3 protons, it's going to give you a singlet that integrates for 3 protons, but its chemical shift is going to be 0.9 plus the 3, right? Because it's alpha to the oxygen of an ester. So it's going to give you 3.9 ppm. So again, the conclusion is just based off of the methyl group that integrates for 3 protons in each case. One of them has a much higher chemical shift, almost double that of this one here. So that's an easy way to distinguish between those two. If we look at these two cyclic ethers, how would we distinguish between those two? I think by now you're probably getting the hang of the fact that there's an axis of rotational symmetry here and here. But in the first compound, you see that these 2 methylenes are chemically equivalent, as are these 2 methylenes. So that means that this compound is only going to give us 2 signals. However, this 6-membered ring here, you see that we have these 2 protons, which are chemically equivalent, as are these 2, but there's also 1 more methylene down here. And so we would end up with 3 signals for this compound. The last one is 2 aromatic compounds. It's pretty clear, I think, that in this compound, I have an axis of rotational symmetry. If I rotate this 180 degrees, I end up with the exact same molecule. And thus, these 2 protons and these 2 protons are going to be chemically equivalent based off of that rotational symmetry. I also have a third unique proton from the alcohol. So I end up with 3 signals here. And in this compound here, there's no symmetry at all, no symmetry. And so each proton on the aromatic ring is in a completely unique environment. And on top of that, the proton on the hydroxyl is also in a unique environment. So if I tally up all those, I have a total of 5 signals. So I would end up with 5 signals for this compound. There we go. Give me a thumbs up if you follow me on that. Even if you're thinking, you know what, I need to take a look at it a little bit and practice it. All right. Okay, good. All right. Seems like my students are following me on that. Well, what would you do when you're faced with an NMR spectrum? You know, it might be a little daunting when you're first starting out, and I just throw an NMR spectrum at you and I just say, you know, try to determine the structure of this molecule. What's the steps that you would want to take? This is a strategy for solving spectral problems, really, or spectra problems. First step is, if you're given a molecular formula, I would always start by calculating an HDI. Right, if you have oxygens and you have an HDI of 1, that could suggest that you've got a ketone or an aldehyde. Or, you know, if you have no oxygens and you have an HDI of 1, then you have a ring or a double bond, right? That's the kind of connections that you want to draw there. After that, you're going to take a look at the number of signals and the integration. That's going to tell you or give you a clue as to whether there's symmetry in the molecule. We saw this in the problem here. Whenever we had symmetry in a molecule like this, or like this, or like either of these, whenever there was symmetry in the molecule, it cuts down on the number of signals. So when you have few signals, oftentimes it gives you clues as to whether there's a plane of symmetry or an axis of symmetry in the molecule. Next, you're going to look at the signal, right? You're going to take a look at each signal in terms of its chemical shift and determine what kind of de-shielding effects this signal is experiencing. You can draw fragments. So if you think you've got a tert-butyl, just write it down. If you think you've got an isopropyl or an ethyl, just write it down. And then what you're going to try to do is put all those puzzle pieces together into a complete structure. If you're the kind of person who enjoys things like crossword puzzles or Sudoku, maybe any kind of problem solving, you are really going to enjoy NMR spectroscopy, because none of the problems will be provided in such a way that the answer is just going to be handed to you on a platter, right? You have to be able to put everything together to come up with some kind of reasonable structure. Also, I want to add one more thing here. Besides a complete structure, I want you to make sure that your structure makes sense. If you start drawing carbons that have 5 bonds or oxygens that have 4 bonds, and I've seen that kind of thing before, that is completely unreasonable. Okay, I don't mean to sound like a meanie or something, but at this point in organic chemistry, you're almost through your first complete semester of organic chemistry, a second year university course. You should know what type of bonding oxygen, carbon, hydrogen have, right? If I see 2 bonds to a hydrogen, well, that's a big no-no. So make sure that your structure makes sense. And then at the very end, what's great about spectroscopy is that you can always check it, right? You can always say, does this answer make sense? Well, that covers proton NMR. The last section of this chapter deals with carbon-13 NMR. And some books will even present carbon-13 NMR before they present proton NMR. And the reason why is because when we looked at proton NMR, we talked about chemical shifts. We talk about splitting, right? Doublets, singlets, triplets, all that stuff, and integration. Well, the thing is, when we're talking about carbon-13 spectroscopy, we're only going to deal with chemical shift. We're not going to take a look at splitting or integration. They are not covered in carbon-13. There are techniques where we can look at splitting, and there's some inferences that we can make about the number of carbons based on the height of a signal, but that's neither here nor there right at the moment. So again, because protons are by far the most abundant isotope of hydrogen, or hydrogen 1, we see strong NMR signals. Usually it takes very little sample to get a good NMR spectrum, whereas carbon-13 is only about 1.1% abundant, right? The most abundant isotope of carbon is carbon-12. And so you have to have a more sensitive receiver coil or a more concentrated sample. Usually what we try to do is run more concentrated samples when we want to run a carbon-13 spectrum. So again, all we're going to see are singlets, if you will, okay, single peaks, and we're just going to analyze them based off of their chemical shift. So there is splitting between carbon-13 nuclei and protons. However, normally the splitting is not just between neighboring protons. It can be to protons that are 2 and 3 carbons away. So then you just end up with something that is really complex and basically becomes unreadable. So what we do is we run what's called a decoupled spectrum. And all that means is that each unique carbon signal will produce a singlet. It means nothing fancier than that. I'm not going to ask you, what's the definition of decoupled? 90% of the spectra that we're going to look at in terms of carbon-13 will be decoupled spectra. So again, you just see singlets. There's no coupling. There are experiments where you can do coupling. The ACS does have questions that involve those, but you know how little I like to use the word simple in organic chemistry. Well, I'll tell you that the coupled spectra are actually pretty simple, and I can explain that to you. Let's take a look at the chemical shifts of a carbon-13 NMR. First of all, we saw that the range of chemical shifts for protons in a proton spectrum was around 0, where TMS is our reference, to about 12 parts per million. And we know that it can go outside of that, but that was generally the range that we look at, 0 to 12 parts per million. Well, carbon-13 signals or carbon-13 nuclei resonate over a much wider range of frequencies, and so their chemical shifts will range from 0 to 220 parts per million. So you can see right away that we don't superimpose carbon and proton spectrum on top of each other or anything, right? The range of chemical shifts is just so much greater for carbon-13. Every signal, which is going to be a singlet, okay, no splitting to worry about, every singlet that we see in a carbon-13 spectrum is going to represent a unique type of carbon. So that means if you have two carbons that are chemically equivalent, they're only going to produce one signal, right? We saw the same thing when we looked at proton NMR. We said that planes and axes of symmetry caused protons to be electronically or chemically equivalent, and the same thing applies to carbon. Let's take a look at an example. Getting back to those same three molecules that we started with on the second slide that we took a look at this morning, right? We took a look at orthoxylene, metaxylene, and paraxylene. Okay, the author of the book seems to really like these molecules because they do such a good job at demonstrating how the number of signals is affected by symmetry in a molecule. Again, you can see that there's a plane of symmetry in the first two compounds, but using a same type of methodology that we used for proton NMR, you see that this carbon and this carbon are chemically equivalent, as is this carbon and this carbon, right? Same thing for these two carbons and the same thing for these two carbons. And so we end up with a total of 4 signals. I'm not going to analyze the next two in detail. I think by now you've probably got the hang of it, but based off of the plane of symmetry, or the axis of symmetry, I should say, in the second compound, we have a total of 5 signals, and there's 2 axes of rotational symmetry in paraxylene, aren't there? Right, 2 axes of symmetry, and so we only end up with 3 unique types of carbons. Right, you remember that this molecule, with respect to protons, I only had 2 signals, right? But remember, on this carbon right here, okay, this carbon that I've circled in red, there are no protons on that, but it is a carbon, so it does count, and we're going to get a signal for that. All right, so again, the number of unique carbons it's going to produce are going to be proportional to the number of signals that we see in the carbon-13 spectrum. Also, if you go back to the proton in your mind, you remember that the table that I showed you of chemical shifts was actually pretty big, right? It was a big table, had all kinds of different chemical shifts in it. Well, when we look at the chemical shifts of carbon-13 atoms, we see that we have a much smaller table of chemical shifts to be concerned with, okay? Just like with a proton, we see that carbon-13 signals are also affected by shielding and deshielding, right? I'll even skip right to the end here. I was going to start at this end, but I'll start at the opposite end. You take a look at the carbon of a carbonyl. It's the one that's going to resonate at the highest frequency and have the highest chemical shift. Why? Because you have the electron withdrawing group, right? The carbonyl attached or the oxygen attached directly to the carbon, so that has a strong electron withdrawing effect, which causes them to be highly deshielded and thus resonate at a higher frequency and thus have a higher chemical shift. If we go all the way down to the bottom of the barrel, right, sp3 hybridized carbons are not going to be heavily deshielded, and so those are going to resonate, or those will have absorbances between 0 to 50 parts per million. sp hybridized carbons and carbons that are attached to electronegative elements like oxygen or nitrogen, those are generally going to come out in the 50 to 100 range. And sp2 hybridized carbons, aromatic or vinylic, those are going to end up in the range of 100 to 150 parts per million. Again, I'm going to give you this for your quiz. I will give you this on your handout, this table. However, for your final exam, you will not be provided with this table. So you'll be expected to know this table for your final exam. All right. Let's move on from there. And the last section deals with depth carbon-13. And this is a very short section, but if you look at a carbon-13 spectrum, which just has singlets in it, there are ways to distinguish between the types of carbon, right? Because there's 4 types of carbons that we can have in a molecule. We can have a quaternary carbon, right? We can have a methine, a CH. We can have a methylene, a CH2, and we can also have a methyl group, right? A CH3. And so we can distinguish between these types of carbons, whether it has no protons, 1 proton, 2 protons, or 3 protons attached to it by running different experiments. The first type of experiment is called a depth 90. Depth just stands for distortionless enhancement by polarization transfer. You can imagine I'm not going to ask anything about that, okay? But in a depth 90, the only thing that you see are methynes, okay? Only, remember this is called a methine. It's the only thing you see. So if you run a carbon-13, just a regular decoupled carbon-13, and you see all the peaks, okay? You see all the signals for each unique type of carbon. Then if you run a depth 90, any signals that you see, you're going to know that those are methylenes. Therefore, you go back to the original spectrum, whichever peaks have the same chemical shift as the ones in the depth 90, you know that those are methynes. Next, you can run another experiment called a depth 135. In a depth 135, all the methyl groups and methynes are going to be pointing up. So positive just means they're pointing up on your spectrum. And anything that's a methylene is going to be pointing down. And so just by running these 2 experiments and a regular decoupled carbon-13, you can distinguish between all the different types of carbons. Because if you look at a methyl and you run all 3 experiments, you're going to see it's going to be distinguished from a methylene, from a methine, and from a quaternary carbon, right? They all have unique signals when you compare the broadband decoupled, the depth 90, and the 135. So if you run all 3 of those experiments, you're able to distinguish between all the different types of carbons that you have. All right, I'm going to skip the part on MRI for now, and I want to move ahead and take a look at some practice problems. So just give me a second here. And where are they? Nope, didn't want to take a look at those. Since you guys have the solutions to these ones, I wanted to take a look at. Here we go. These are the ones I wanted to take a look at. So again, these are on Canvas. If you look at the Chapter 15 module, yeah, they're right there. So if you go to the Chapter 15 module, it says Chapter 15 problems, practice problems V3, I think is what it says. So if you want to print these out or put them on a tablet or something, yeah, they're posted up there right underneath the file that says a strategy for solving spectra problems. So I'm going to give you a second to take a look at the first couple of problems here. Just give me a second here. I'm trying to download the handout that I'll give you for the quiz. Just give me 2 shakes of a lamb's tail and I should have it. I just want to post it to the chat for you. So let's see here. Upload from my computer. Okay, so if you go in the chat right now, you'll see, I think you'll see a PDF there. It should be there now. It says IR NMR Tables Klein. That is the handout that you will be allowed to bring with you to the quiz on Monday. So when you're doing your practice problems, feel free to have that with you all the time. You see that the first part deals with IR absorbances. Now, we've already covered chapter 14, which deals with infrared spectroscopy. But if you look below, we have the typical values for proton NMR chemical shifts. And below that, we have the typical values for carbon-13 chemical shifts. So those are the 2 tables that are going to be most pertinent to you for the chapter 15 quiz. All right. Well, let's take a look and get organized here. Okay. Okay. Let's take a look at the first question, and we'll try to walk through some of these. So your participation is greatly appreciated. And let's start with the first question. So it says protons HA and HB in the following compound are, would these 2 protons be homotopic, enantiotopic, diastereotopic, mesotopic, or none of these? Anybody have an answer for this one? Yeah, they're diastereotopic. Probably one of the easiest ways that you could figure this out is to do the replacement test. So if you're not following my students who answered this one pretty quickly, let me just show you quickly how to do the replacement test. And if I'm going too slow, feel free to go ahead and keep looking through the problem. So if I just start by drawing the skeleton of the molecule, I'll try to draw it a little prettier than that. Here we go. That's better. So if I draw the skeleton like this, and then I do the replacement test, if I have a hydrogen here, and if I replace it with the deuterium, the other hydrogen, and then I look at replacing the other hydrogen, or swapping them, so to speak, what do I end up with? You see that I have one chiral center that is remained unchanged, but the other chiral center is flipped. And so these are not enantiomers, these are diastereomers. And thus, the 2 protons, HA and HB, are in fact, as my student said, they are diastereotopic. All right, let's take a look at protons HA and HB in the following compound. My first question to you guys about question number 2, the molecule is there a plane of symmetry in this molecule? Is there I keep saying plane when I mean an axis. Could anybody tell me? So yeah, I have some yeses and some nos. Could anybody tell me if there is an axis of rotational symmetry, how many axes of rotational symmetry are there in this molecule? Yeah, there are actually 2 axes of rotational symmetry in this molecule. So I'm going to make a model here to prove it to you. I thought I was going to make a model. What am I missing here? There we go. Just give me a second. And again, if you're ahead of me, feel free to keep moving forward. No problem there. So I'm going to build a model here. Just give me a second. Almost done. I tried to look to see if I could buy a model kit like mine the other day. And they don't make them anymore, so that was kind of disappointing. Since it's my favorite. Good. Thanks, Skylar. Thanks, Byron. I just want to stop the thing here and show you on my camera. Okay, here's this molecule. Back up here. Oops. There we go. Okay, here's that molecule. Here it is right here. And the way that they have it in the page is that they have this methyl group going down and this methyl group going up, like that. Right? That's the molecule that they're showing you in the question. But remember, if you turn the molecule like this, right, there's free rotation about the carbon-oxygen bond. And so you can see that there's an axis of rotational symmetry going this way, and there's also an axis of rotational symmetry going this way, right? We have axis of rotational symmetry this way, and we have it that way. Just because they put the bonds going up and down like that, that is of no consequence. You have to understand that there is free rotation around a carbon-oxygen bond, right? That's a single bond, and therefore you can see the plane of symmetry. And when you put the molecule like this and put both of those methoxy groups coming out like this, then you can see the other axis of symmetry like that. So we have two axes of rotational symmetry. Let me get back to my screen. There we go. Can you guys see my screen again? My slide here? Good. Thanks, Jonathan. Perfect. So yeah, there's two axes of rotational symmetry. If it helps, something that you may want to do is just try redrawing the molecule. If we redraw the molecule like this, right, you see you have OCH3 like this, and you have OCH3 like that. Maybe that helps. But yes, there is an axis of rotational symmetry here, and there's another axis of rotational symmetry here. And so those two protons are homotopic. They are chemically equivalent. Okay, let's move on from there. How many signals did you expect to see in the proton NMR spectrum of this is called ethyl methyl ether? Let's draw the compound out as a bond line structure. We have this and this. There we go. So we have a methyl group on one side, and we have an ethyl group on the other side. Well, all of the protons in the methyl group on the left, those are all chemically equivalent. They are not coupled to any other protons. And so we would see a singlet for that. So that's a signal. Then we have an ethyl group over here. Hopefully, after last lecture, you get the point that this methylene is coupled next to 3 protons. So this will produce a quartet. And the 3 protons in the methyl group, which are chemically equivalent, are coupled to these 2 protons. 2 plus 1 gives you 3. And so this is going to give you a triplet. Singlet. And so we end up with a total of 3 signals in this molecule. Again, if I'm confusing you on anything, make sure to stop me because I want to get into carbon in a little bit here. How many signals would you expect to see in the proton NMR spectrum of this glycol? And a glycol is just a molecule where you have 2 hydroxyl groups, and we'll talk about glycols in organic chemistry too. But if I draw out this molecule, I have 1, 2, 3, 4 carbons. Then I have a hydroxyl here, and I have a hydroxyl here. It might not be abundantly clear from the way that it's drawn like this, but if we draw it like this, okay, if we draw the molecule like this, and there is free rotation around all the carbon-carbon bonds, you can see that there is an axis of rotational symmetry. And thus, these 2 sets of methylenes are going to be chemically equivalent, as will these 2 sets of methylenes be chemically equivalent, and the 2 hydrogens will be chemically equivalent. And so we're going to see a total of 3 signals for this compound due to the plane, sorry, I keep saying plane when I mean axis of symmetry. Let's move on from there. How many signals would you expect to see in the proton NMR spectrum of the following compound? I'll throw that out there to my students. Give you a second. If anybody's got an answer, just throw it up on the screen. How many unique types of protons would there be in this molecule? I can redraw it here. Yeah, some people are giving me some big numbers. I see that Skylar and Stephanie are both saying 7. I think you're in the right vein because there is no symmetry in this molecule. None. There's no rotational symmetry. There's no reflectional symmetry. And so we have 4 protons on the aromatic ring, don't we? We have this proton, we have this proton, we have this proton, and then we have another proton here. You can see that each one of those protons is in a chemically unique environment, right? None of them are equivalent. There's no way I can flip this molecule around and superimpose one proton upon another. So I get 4 signals from those, plus obviously the proton on the carboxylic acid is unique. There's no other carboxylic acid in here. And then I have an ethyl group over here. And so this methylene, those 2 protons are going to give one signal. They're going to give you a quartet. And then this methyl group here is going to give you a triplet. And so I have a total of, let's count them. We have 1, 2, 3, 4, 5, 6, 7. The answer is we end up with 7 signals. I have a question for you guys. Okay, this isn't the question that's asked here, but could anybody tell me how many carbon-13 signals I would see for this molecule? How many different types of carbons are there in this molecule? And it's not a trick question. All right, awesome. All my students answered correctly. Perfect. I'm not going to redraw the molecule, but yeah, you see that again, there's no axis or there's no rotational symmetry in the molecule. So I'm going to use the green highlighter to highlight all the unique carbons. Look, I have 6 carbons in the aromatic ring. Each one of them is different, right? They're all in different environments. There's no symmetry. So I have 6 there, 7 for the carbon in the carboxyl group, 8 and 9. So I have a total of 9 signals. Awesome. That's amazing. Great. Okay, let's move on from there. Number 6 says, which of the indicated protons in the following compound would appear most downfield? Remember, if the proton is appearing more downfield, that means it's the most deshielded of all of the protons. This is not a trick question. Who could tell me which one would be the most deshielded? The one that would give you the highest chemical shift? Yeah, good. Okay, the answer is number 4. Absolutely. It's going to be this one here. What would be the approximate chemical shift? Well, it's a methylene, so it's 1.2. Plus, it's alpha to an oxygen from an alcohol, so we add 2.5 parts per million to that. So that would give us around the neighborhood of 3.7 parts per million. Anyhow, that's neither here nor there. It's not what they're asking. But yeah, it's number 4. Okay, let's try some estimations here using that table. I can't remember the number of the table off the top of my head, but let's take a look at this problem. It just says, which of the following is the best prediction of the chemical shifts for the signals of the proton NMR spectrum of this compound? Let's start with the methylene. Number 1, what would be the chemical shift for those 2 protons? Well, the baseline for a methylene is 1.2 parts per million, plus it's alpha to this oxygen, so that means I'm going to add 2.5, and again, that's because it's alpha to the hydroxyl. Then you notice that it's beta to the carbonyl, and so I have to add 1/5 of 1 to that, which would be 0.2, 0.2. So that's 1.4 plus 2.5, so that gives me 3.9 parts per million. The next one, I'll just do it over here. So number 2, what's the chemical shift of number 2? Well, the baseline for a methylene is 1.2 parts per million. This one is alpha to the carbonyl, so we're going to add 1.0, and then it is beta to, it's beta to the hydroxyl, so we add 1/5 of 2.5, so we're going to add 0.5 to that, and we end up with 2.7 parts per million. And then for number 3, we have a methyl group. The baseline is 0.9 parts per million, and it's alpha to the carbonyl, so we're going to add 1. It is not beta from the hydroxyl, so the hydroxyl has no effect, and so we end up with 1.9 parts per million. Now, which answer is that? So number 1 is 3.9, so it's going to be one of these. Number 2 is 2.7, and number 3 is 1. So it must be C. There we go. All right. This one is a problem that I've done before with my class, and I'm not wild about this problem. I'll tell you why. I got this from a question bank, and I've measured these step curves a hell of a lot of times using a ruler. So if anybody, I know that I've taught this class long enough to know that in 2021, there's probably somebody out there who's looking at this on a tablet right now and drawing on a tablet just like I am. I don't expect that person to whip out a ruler and start measuring something on the screen. However, if you did print it out and you try measuring it, and I've done this Avogadro's number of times, you end up with, this is around 9 millimeters. The next step curve, I got 37.5 millimeters approximately. And the next one, I got 12 millimeters. Okay, so since there's no integration values here and you want to compare the relative number of protons, look, I've done the math on this so many times. If you divide 9 millimeters by 9 millimeters, you get 1. If you divide 12 millimeters by 9, you end up with what? 1.3, right? 1.33333, right? If you take 37.5, you divide it by 9, you end up with 4.2. Now that they're not great numbers to work with, in my opinion, because if you multiply this one here, so 1.33, if you multiply that one by, what would it have to be? So you take 3. So if you multiply that by 2 and a bit, right? If you multiply this by, let's say you multiplied it by 2.2, and I'm just kind of doing this for the first time here, 1.33 times, and you'll see why I'm not crazy about this. You'd get a number that's pretty damn close to 3. If you multiply this by 2.2, you would end up with 2.2, but that's pretty close to 2. And then if you take 4.2 and you multiply it by 2.2, you end up with something that's, close to 9. And that's the actual answer. That is the supposed answer. 3, 9, and 2 are the relative numbers of protons. So the first signal represents 2 protons. This one represents 3 protons. And this one here represents 9 protons. It kind of looks to me like these two have the same coupling constant, and they probably do come from an ethyl group, right? And the one that integrates for 9 protons, that's a big singlet. That's probably a tert-butyl group. Here's my take-home message from this as your instructor. Okay, I'm the one who writes your quizzes. I would not give you a question where the numbers don't work out better than this. Okay, if I ask you to calculate integrations based off of, I'm not going to give you a step curve, but if I give you integration values, they're going to work out a hell of a lot better than these. Anyhow, but that's how you work out the problem. You measure the step curve, right? And I went over this with you in class. You measure from the 2 horizontal lines of that step curve and this one, and then you do the same thing here with a ruler. Anyhow, all right, when I was an undergraduate student, we did that a lot, but I also have a chemistry degree and took an entire class on spectroscopy, so my memory's probably not perfect. I probably did it a lot in that class. Anyhow, question number 9, which of the following compounds gives a proton NMR spectrum consisting of only a singlet? So if we look at all these different compounds, A is what? 1,1-dichloropropane, so that would be this compound. It's not very pretty, is it? That's a little better. B is what? 1,3-dichloropropane, so if we have 1, 2, 3, like that. C is 1,2-dichloropropane, so if we have something like this. Not a lot of space here, is there? That, and then D is what? D is 2,2-dichloropropane. I'll just throw this out there to my students in the interest of time. Does anybody have an idea which one of these would only give one singlet? Which one of these would give one singlet? We've looked at compounds that don't have a lot of signals. Yeah, the answer, Autumn and Skylar, yeah, you both have the right answer. It's D, because D has an axis of symmetry, right? But these two methyl groups are not split by any protons, right? Because this carbon has no hydrogens attached to it. And so both of these are going to give a singlet, right? The same singlet. If you look at this compound here, 1,3-dichloropropane, there is an axis of symmetry in the molecule. However, there's two types of protons, aren't there? There's these two, and then there's also this one. So this compound would actually give you 2 signals, and the other ones are way off. The other ones would both give you 3 signals, right? You have this being, this being a unique signal, this one's unique, and this one is unique. The same thing here, this one, and this one, and this one, they're all unique. So both of those would give you 3 signals for this one or this one. Okay, let's take a look at, I want to skip ahead here. Just what time is it? 8:49. I want to skip ahead to question number 19. And I'll post the solutions to these problems for you. But I want to skip ahead to question number 19 because I want to take a look at some problems that deal with carbon-13 spectroscopy. Which of the following compounds is consistent with the carbon-13 NMR spectrum shown below? This is a carbon-13 NMR spectrum. You see that it ranges from 0 all the way up to around 220 parts per million, as I told you. And we also saw that we can cut this up into 4 different regions, right? We said that 0 to 50, the 0 to 50 range, that was for sp3 hybridized carbons. The range from 50 to 100, this is for carbons that are attached to halogens, or carbons that are attached to oxygens, or carbons that are attached to nitrogens, or carbons that are in triple bonds. The range from 100 to 150, this is for aromatics, okay, aromatic carbons or vinylic carbons. And then the top range from 150 and above, that's going to be for carbonyls. So this is for a carbon attached to a carbonyl. So we got 2 sp3 hybridized carbons. We've got some aromatic carbons. And what else? We have a carbonyl. Well, how many signals are there in this spectrum? I'm going to zoom in here. You can clearly see that I have 2 signals just above 20. But in the aromatic region here, you can see that these are actually 2 different signals. So I have 1, 2, 3, 4, 5, 6, and then I have a 7th signal out here. That means that we have a total of 7 signals. So 7 signals for our molecule. Now, if I go back down here and I look at the possible structures, is there anyone that you would eliminate right away that doesn't have 7 signals? I'm curious which ones you guys might eliminate quickly. Yeah, somebody says 2 and 3. I see there's a big problem with number 2, right? I have a unique carbon here. I have a unique carbon here. I see that these 2 are chemically equivalent based off of rotational symmetry. I see that these 2 are chemically equivalent based off of rotational symmetry. And I see that this is a unique carbon, and this is also a unique carbon. So I have a total of 1, 2, 3, 4, 5, 6 signals for that one, right? This one is going to produce 6 signals. So that can't be an answer. Number 3 has a total of what? I've got a unique signal here. I have another unique one here. another one here. And in fact, every carbon in the ring is unique because there's no axis of symmetry. So I can just keep going around my ring like this, and I see that I have all of these as being unique carbons. So I have 1, 2, 3, 4, 5, 6, 7, 8. So I have one too many signals here. I have 8 signals. Okay. Could anybody tell me how many signals are in number 4? Well, maybe I'll go a little quicker. Oh, yeah, I think Autumn answered. Sorry, I didn't see your answer, Autumn. There's a total of 9 signals. I'll go a little faster. Look, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 signals. There is no axis of symmetry. A student asked, could I eliminate numbers 2 and number 3 based on the fact that there's no carbonyl because I have to have a carbonyl? Absolutely. You could just say no carbonyl. Therefore, they aren't possibilities. I just wanted to review the number of signals, but that is definitely a faster way of doing it. Okay, so the answer is going to be number 1. Let's take a look at it. I've got the 2 sp3 hybridized carbons, right, which would be the 2 methyl groups. I have the carbonyl, right, which is going to be this one up here. I have 2 quaternary carbons, this one and this one. Those are going to be these 2 right here. Now let me show you something very quickly. You see that I have 2 chemically equivalent carbons here, and I have 2 chemically equivalent carbons here, right? Those are going to be these ones, okay? It's these 2 right here. Now I told you that there's no such thing as integration in a carbon-13 spectrum. However, if you look at the relative height of these signals, normally when you have more of a type of carbon, right, if there's symmetry, since there's only one carbon represented by this signal and there's only one carbon represented by this, each of these, you could probably guess that each of them is the result of 2 carbons, okay, each of those signals. And we see that that's actually the case. We have 2 carbons here and 2 carbons here. Okay, you can't always hitch your wagon to that. It's not going to work out 100% of the time, but it does work out a heck of a lot of the time. All right, number 20. Which of the following compounds is consistent with this carbon-13 NMR spectrum? Notice that there's no absorbances above 80 parts per million, and so they just cut that part of the spectrum out. We've got 3 signals here, don't we? Come on, Ben. We've got a total of 3 signals, right? We've got something from the 0 to 50. These ones are sp3 hybridized. And then the one up here, since each one has an oxygen, they're all alcohols. This is a carbon that's attached to an oxygen. We know that just by process of elimination because all 4 of these compounds, again, are alcohols. What about number 1? Number 1 is impossible, right? Because number 1 is going to have 1, 2, 3, 4, and 5 different types of carbons, right? Those are all unique. I end up with 5 signals for this compound. So it can't be number 1. What about number 2? How many types of signals would I see in number 2? I'll just throw that out there to my students. How many signals for number 2? Somebody says 5, somebody else says 5, somebody says 4. Well, if you look at making a model of this compound, since there is free rotation around this carbon-carbon bond, these 2 carbons are chemically equivalent. Okay, those 2 methyl groups are chemically equivalent. We have those 2 as being chemically equivalent. This carbon is unique, this carbon is unique, and this carbon is unique. So we have a total of 1, 2, 3, 4 signals for this molecule. 4 signals. If you want to draw this a different way, I'm just trying to think of a way that I could draw it that might make it simpler for you. If you draw it like this, okay, and draw the two methyls coming down like this, if you draw the hydroxyl coming straight out towards you, and you draw the ethyl group in the back, right? If this is your ethyl group, then maybe it's easier to see that there is a plane of symmetry running through the molecule that makes these two methyl groups chemically equivalent, right? You can clearly see that the yellow carbon, this one here, is not a stereocenter. And so that renders those two methyl groups chemically equivalent. Does that make sense to you? To anybody who answered 5? Just want to be sure. If not, I can make, okay, thanks, Stephanie. If not, I could make a model for you. I could cobble it together. But you know what? That's something you guys could try too. If you bought even the most inexpensive model kit, even some Tinker Toys would work to show you that those two methyl groups are, in fact, chemically equivalent. Okay, so we get 4 signals. What about number 3? I bet you in number 3 it was more clear. It was even clearer to you that these two methyl groups are chemically equivalent, aren't they? Right? Those two are chemically equivalent. This one is unique, this one is unique, and this one is unique. So we have a total of 4 signals for this guy as well. 4 signals. So we can cross off number 2, and it must be number 4. And yes, there's certainly a plane of an axis of rotation through the molecule. This carbon is unique. However, these two are chemically equivalent, and these two are chemically equivalent. And so for this molecule, we see 3 signals. Does it make sense? Let's draw the compound out here. This is called 3-pentanol. The way that we annotate a carbon spectrum is we start out here. We say A, B, C, and we start going backwards like that. So which ones of these carbons would be the least deshielded, right? Which ones would be the most shielded? It would be the two that are the furthest away from the oxygen. So this would be an A carbon. This is an A carbon. I'll move it a little ways away from here. There we go. And what else? I have my B carbons here and here, and then this would be the C carbon down there. Notice again that the height of these two is about 2 times, right? Both of these are about 2 times the height of this one. Does that make sense? Yes, because there's twice as many A and B carbons as there are C carbons. There's only one type of C carbon, and there's twice the amount of B's and A's, right? Just like putting a puzzle together. Isn't it fun? Let's try another one. I'll give you a second to look at this and see if you can come up with an answer. Okay. Trying to figure out what to answer. For my students that answered B, or the second one, how many signals would there be in that compound in number 2? In this spectrum, we have a total of 4 signals. Yeah, in number 2, all 3 of these carbons are chemically equivalent. This one is unique, and this one is unique. So for this compound, you'd only have 3 signals, and you have a total of 4. I'm trying to figure out in my mind why you guys would have guessed that one. I'm wondering if it's because you saw, and you can't answer this without, it's hard to answer this over Teams, but I'm wondering if it's because that's a T-butyl group and you saw this big peak down here, this big signal down here. That's with proton, right? You see a big singlet that integrates for 9 proton, but remember, this isn't a proton, this is a carbon. Anyhow, maybe I'm off in left field. I could be totally wrong. The first one, you see that there's a total of 5 signals there, so that's totally wrong. It's just plain wrong, right? But I see a bunch of students are answering number 3 now, and you can see that these two are unique. This one is unique. This one is unique. And didn't we go over this already? Yeah, so there's 4 signals for this one. if I draw the structure of this alcohol, okay, and I label these signals A, B, C, D, you always start from the right-hand side of the spectrum and you just use the alphabet A, B, C, D. And the reason why is so that everybody gets the same annotation. Everybody annotates a carbon spectrum the same way. It doesn't matter if you're here, if I'm at my house, you're at your house, or somebody's in a different state. You always end up annotating a spectrum. If you've done it correctly, they should always be the same. So A would be these two carbons here, which are chemical equivalent, and it makes sense because this is about 2 times the size of all the other signals, which only represent one carbon. B, B could either be this one here or this one here, as well as C. If we take a look at those, okay, you might not be able to distinguish between those two right now, so we'll put B and C, unsure. When we do chemistry 3102 analysis of carbon, I'll show you how to distinguish between those two. I don't know if our book does it or not, but then you can see that D is the one that must be attached to the oxygen, and so we'll put that up there like that. There we go. And let's take a look at 22, which deals with a depth spectrum and asks us to elucidate the structure of a molecule. A compound with this molecular formula, C5H10Br2, displays the following carbon-13 along with depth 90 and a depth 135. Carbon-13, what is the structure for this compound? So we have C5H10Br2. Remember that a bromine has the same value of a hydrogen, so this is as if you had C5H12. If it's C5H12, that's like having N and then 2N plus 2. So that means the HDI of this compound is 0. There's no double bonds in this molecule. Okay, there's no rings in this molecule. What else do we see? We have 5 carbons in the molecule, but in the broadband decoupled that shows us everything, we only have 3 signals. Okay, so we have 3 signals in the broadband decoupled. Remember that at depth 135, in a depth 135, all the CH2s are pointing down. Anything that's a methyl or a methine is going to be pointing up. And in a depth 90, we have only CHs. Therefore, there are no CHs, right? There's no methynes in this molecule since there's no signals in there. And you can see that every one of these 3 peaks, right? This one, and this one, since they're all pointing down in the depth 35, all 3 signals are CH2s. They're all methylenes. So 3 signals, and they're all methylenes, CH2s. Based off of your nomenclature prowess, because we did look at the nomenclature of alkyl halides, and this must be an alkyl halide because it's only got carbon, hydrogen, and bromine in it. Could anybody name the molecule? I can't ask you to tell me what the structure is, or you could try to describe it maybe. This is where it would be easier if we weren't in the middle of a global pandemic. But could anybody name this molecule or give me an idea? If there's only 3 signals in the molecule, there must be a plane of symmetry, right? So we could put that in here. There must be symmetry. It's not a ring. It can't be a ring because the HDI is 0. So if the HDI is 0, there is no ring and no double bond. There's no units of unsaturation. 3-bromopentane. So somebody says if I have 1, 2, 3, 4, 5 carbons like this and put a bromine, it can't be that because I have 2 bromines in my molecule, right? It's Br2. So that would not be possible. Yeah, there's only there's 3 unique types of carbons in that molecule, but that can't be the compound. Yeah, that sounds better. So, Autumn, you were in the right vein when you said I must have something like this. right? Because I've got one CH2, two other CH2s that are chemically equivalent, and these two CH2s that are chemically equivalent. So the way that you round this out is you have to put a bromine on this end and a bromine on this end, and you end up with 1,5-dibromo pentane. And that would be the molecule, 1,5-dibromo pentane, right? And you notice that the green carbons must be the ones that are the most deshielded because they're the ones that are attached directly to the bromine. The blue carbons would be this one here, and the yellow one would be this one here that is the most shielded, right? There we go. So that's how we use a carbon-13, a depth-90, and a depth-135 to solve for the structure of a compound. Give me a thumbs up if that makes some sense to you. Even if you're like, you know what, I think I could figure that out. Yeah, again, if you're the kind of person that likes puzzles, you'll really enjoy NMR spectroscopy. So those are some examples of carbon-13 problems. And of course, in the textbook, I have picked out more problems that deal with carbon-13. And of course, the solutions manual is available to you. Let's back up and go right back to question 10 and turn our attention. No, let's try question 16. This is a good one. I want you to read question 16. It was one of the questions I looked at this morning. And while you're thinking about it, I'll make a model of it. Model. You guys probably don't know where Newfoundland is, but anyhow, that's my best Newfoundland accent. Making a model. All right. Where are my students? Could anybody answer question 16? How many signals would there be in the carbon-13 for this compound? So how many unique types of carbons are there in this molecule? All right. Let's see, what do my students put? All kinds of answers. Good. Most people put, or the two people who answered, put 9 carbons. Okay, so let me show you how to solve this one. Because of free rotation around this carbon-carbon bond, right? I can rotate that bond. That means that these two carbons in the aromatic ring are chemically equivalent, as are these two compounds. Carbons are chemically equivalent. Then I have a unique quaternary carbon here, and I have a unique quaternary carbon here. So from my aromatic ring, I get a total of 4 signals. Now, what about all this spinach out here? Well, hopefully you can tell that the 2 vinylic carbons are unique because this carbon that I just highlighted in yellow is attached to this aromatic ring and this methyl. So it's definitely unique. There's no other carbon like it. And this vinylic carbon is also unique, right? There's no other carbon like it in the molecule. This carbon is also unique, and usually where students run into problems is with these 2 carbons, and they think that they might be chemically equivalent. These 2 carbons are not chemically equivalent. Let me show you with a model quickly here. Quickly. So where's my camera? Okay, so here's the model of, oops. Here's the model of that molecule. How do they have it in the book or in the picture? They have it like this, okay? But because there is free rotation around this carbon-carbon bond, right, that means that I'm only going to end up, right, and I'm trying to just rotate this to demonstrate it. Since there's free rotation around this bond, that renders these 2 carbons equivalent and these 2 carbons equivalent. So we get 1, 2, 3, and 4 signals from my aromatic ring. Now look at the double bond very carefully. Right, there's my double bond. You can see the double bond. You can see clearly now that the 2 vinylic carbons are unique. One's got a phenyl and a methyl. The other one's got 2 methyls. Those are different, right? This methyl is unique. It's these 2 methyls here. Look, there's no rotation around a double bond. This methyl group is next to, it's cis to the aromatic ring, and this methyl group is trans to the aromatic ring, right? It's cis to this methyl, and so these two methyls are in unique environments, and that is a problem that I've seen before in this class where students said, "Oh, these two must be chemically equivalent." So it might be helpful for you to redraw the molecule sometimes. And that's totally normal to want to redraw a molecule, you know, just to think about it in a different light. So maybe, you know, it might help if you were to draw the molecule like this, you know, and you say methyl group, methyl group, methyl group, and then I have a phenyl group up here, right? Then I think it becomes much more abundantly clear that all three of these methyl groups, all three of those methyl groups are unique, as are this one and the two vinylic, and then you end up with 4 carbons, 4 unique carbons in the aromatic ring. So 4 plus 5 gives you 9. Okay, that's another one I think is a good one. We got 2 minutes left. Let's try one more problem. Let's try question number 17. I'll just throw this out here. You see, I didn't give myself a lot of space to solve that one. How many proton NMR signals are there in benzene? So benzene is C6H6, and cyclohexane is C6H12. So this is benzene, and this is cyclohexane. How many proton NMR signals are there in benzene? Can anybody tell me? Excuse me. And this is a question we actually looked at in the lecture videos. Anyhow, the answer is 1, right? All 6 of the protons in benzene are chemically equivalent because there's multiple axes of rotation. So all 6 of them are chemically equivalent. And the same thing applies here, right? All the methylenes in cyclohexane are chemically equivalent. They're all identical. And so 1 signal is the answer for both of those questions. 1 signal for cyclohexane and 1 signal for benzene. Thanks, Stephanie. All right.